Hey, welcome back to Calculus. In this video lecture, we're going to take a look at the section 3.2 material on the product and quotient rules. So you can see that the two objectives of the video lecture are written there. We want to know the product rule for differentiation. We want to know the quotient rule for differentiation. Maybe you recall product is just a sort of a synonym or another way for saying multiplying. And quotient is a synonym for dividing. So we already have some rules. In fact, I want to kind of summarize them here. We already know how to differentiate sums. Yeah, our sum rule says that if you take two functions, I'm just going to write briefly here in Newton notation, f plus g, and you want to take their derivative, the sum rule says that you do that term by term. The derivative of a sum is the sum of the derivatives, if you like. We also have a rule for differences. Difference is just subtraction, right? The derivative of a difference is the difference of the derivatives in the same order. So basically, I'm asking in this section, we're asking the question, well, what about for products? What about for quotients? What kind of formulas do we expect for something like f times g prime, f divided by g prime? Yeah. So are there analogs of these sum and difference rules for multiplication? So let me slide down here a little bit. So just rephrasing that question, what kind of formula do we expect for this? Here I've switched over back to the Leibniz notation. I want to get you used to it. But if you like, in the notation that I was writing above, I'm wondering, well, what kind of formula do I expect for f times g prime? Let's start with products. Let's play around with just an example here. I've got an f of x, x squared, and a g of x, x to the fifth. In this particular example, we can work out a formula for what f times g is. F of x times g of x is just x squared times x to the fifth. And by the rules of exponents, x squared times x to the fifth is x to the seventh. Yeah? So we can work out what the derivative, f times g prime, it's a power function. Its derivative is 7 times x to the sixth. So for sums and differences, the rule goes, well, the derivative of a sum is the sum of the derivatives. The derivative of a difference is the difference of derivatives. So maybe for products, the derivative of the product should be the product of the derivatives. So let's just take f prime and g prime separately. F prime is just 2x, f is x squared. G prime is 5x to the fourth. So what do we get if we multiply f prime by g prime? Well, you get 2x times 5x to the fourth. 2 times 5 is 10, and by the rules of exponents, you'd get 10 times x to the fifth, right? So it's different. The derivative of the product is 7x to the sixth. The product of the derivatives is 10x to the fifth. Those aren't the same. Those aren't the same. So the product rule is, just by this example, we haven't discovered the product rule yet, but it's more complicated than sums or differences. And you're probably not surprised. Multiplication is a more complicated operation than addition and subtraction. Okay, so what do we got to do to derive this product rule? We got to go back to first principles. Here I've got just a summary of what we just said in general. I'm not claiming it's never true, but in general, the derivative of a product is not going to be equal to the product of the derivatives. It's not going to be. All right, so what is the derivative of a product? That's what we've got to turn our attention to. So we're going to go back to first principles, and I've written this out because I can kind of narrate it faster than I can write it, and it'll keep the video shorter. But you can pause this and kind of look at it line by line. So I'm going back to first principles of the derivative, and I'll just kind of grab my laser pointer and highlight for you what I'm talking about. So I want to take the derivative of this function f times g. All right, so the limit definition of derivative says I should take f times g evaluated at x plus h, subtract f times g evaluated at x, and divide the whole thing by h. Take the limit of that as h goes to 0. All right, so now I'm going to kind of pull a little bit of an algebraic trick here. Let me show you just by color coding. I've got this f times g, f evaluated at x plus h. It's still in the formula. Yeah, and I've also got, I'll switch the color, I've got this f times g, it's still in the formula with the sign minus. So what did I do? I stuck in a couple of terms. So how can I claim that this quantity is still equal? Notice the terms that I stuck in are exactly the same, except one of them has a plus sign and one of them has a minus sign. So I've just subtracted and added the same quantity. That's what justifies this equality. Yeah, if you subtract something and then add the same thing back, you haven't changed anything. It might not be exactly clear why I decided to subtract and add this quantity, but it will be if we look at the next line. Okay, so you guys are with me? Good. Okay, so moving down a line here, now let's see if I've painted myself into a color coding. Maybe I'll just do it with the laser pointer. If I look at these first two terms, yeah, they both have a g of x plus h in them. So I can factor that out. I'm factoring out g of x plus h, and what's it times? Well, it's times the difference of the remaining terms, f of x plus h minus f of x. Okay, so that's kind of the algebra I did on the left-hand side of the formula. I factored out a g of x plus h. The last two terms in this numerator both have f of x in common to them. So I factored it out. What's left? G of x plus h minus g of x, the quantity. Okay, so that's just algebraically sorting this through. And now some limit laws. I glossed over this earlier. Well, maybe I could slide, but I'm assuming that both f and g are differentiable functions. Yeah, so I'm wondering, under the assumption that f and g are both differentiable, how do I differentiate their product? Okay, so the limit laws justify what I'm doing next. What am I going to do? I'm going to take these two terms, these two things that I'm adding together. I just showed you which two things I'm talking about by drawing laser pointer brackets around them. And I'm going to split that limit across the sum. Both of those terms are divided by h, so I divide each summand by h, and the limit of a sum is the sum of the limits if everything exists. All right, so I'm using limit properties to rewrite down here. So I've got the limit of this first part, limit of the second part. And then more limit properties. It's a busy calculation, but I've got in this first summand, let me just show you what I'm talking about. This first summand, I have a product. Well, the limit of a product is the product of the limits if everything exists. And these are differentiable functions. They're continuous functions, so these limits all exist. So that's what justifies me writing this limit of a product as the product of the limits. Similar in the second one, but I can even say it's simpler, that f of x, this factor, doesn't depend on h. It's a constant with respect to h. So I'm just pulling it through the limit. Okay? So now what have we got? Well, you can probably recognize by these things that we're writing, these limits of difference quotients, those are exactly the derivative of f and the derivative of g, respectively. Those are the limits of f of x plus h minus f of x over h. That's the derivative of f. This thing over here on the right is the derivative of g. F of x is multiplied by that. The last comment I have to make is, why is the limit as h goes to 0 of g of x plus h equal to g of x? That's because g is a differentiable function and hence continuous. So if you're going to take the limit of g of x plus h, you can take the limit inside first by the continuity of g, and x plus h certainly approaches x as h goes to 0. All right, so here we have derived our formula, and let me scroll down and I'll show you the clipping I took out of the book. It looks a little nicer. So we're going to call this formula the product rule for differentiation, if you like. And here the author is being more careful than me and was sure to state that f and g are both differentiable functions. So they both have derivatives that exist at this number x. Then the derivative of the product, well, it's not the product of the derivatives. It's more complicated than that. If we sort of take these things and call f and g, the language I like to use is the first factor and the second factor, because I'm reading the equation left to right. So the product rule says the derivative of a product is the first factor times the derivative of the second, plus the second factor times the derivative of the first. Yeah. Or I think it looks a little nicer in the Newtonian notation. That's all I wrote down here, is that f times g prime is f times g prime plus g times f prime. And of course, there's different ways to write this formula. Multiplication is commutative. I mean, you can rearrange the order. Addition is commutative. So if you prefer, you could write this as g prime f plus f prime g. There's a whole bunch of different orders you could write these things in. You could write g f prime plus g prime f, and so on. It would not knock yourself out. I personally like to memorize it in this form because of the way I read things left to right. When I'm using this formula, I usually just write down the first factor again, and then multiply it by the derivative of the second, and then I write down the second factor and multiply it by the derivative of the first. But there's no natural order. You can write that thing in any way you like. I think the spirit of it is that when you differentiate a product, you get two terms, and in the terms you differentiate one of the functions but not the other, and you have to do that in both possible ways and add them together. I think that's the way I would recommend you try to memorize this formula. Differentiate one of the factors but not the other in both possible ways. Add them together. Let's do a couple quick examples. These examples I'll write with you, so we're going to slow down a little bit, but it'll be okay. So here I want to take the derivative of x to the fifth times e to the x. So I recognize that it's a product rule problem because of that multiplication. X to the fifth is differentiable, e to the x is differentiable, so the product rule says so is this product. And we're using the rule for the first time, so let's write it out in detail. So we're going to take that first factor and multiply it by the second factor's derivative. I'm just going to use the prime notation to make it easier to write. And then I'm going to add to that the first factor's derivative times the second factor undifferentiated, right? So that's my first thing times second thing prime, first thing prime times second thing. And now I'll do the derivative. So I would recommend that when you're doing this, you write these steps out like this, because in that first step, I was just focusing on getting the product rule pattern correct. Okay, now I can let my brain focus on what these derivatives are. It's kind of hard to do it all at once. So the derivative of e to the x, you remember, is just itself. The derivative of x to the fifth is 5x to the fourth, and you multiply that by the e to the x untouched. So in some sense, that's my answer. And I can leave it like this. If you want, you can simplify it. There's some reasons in the future that we'll want to make these simplifications, but you might notice that there's an x to the fourth in both terms. There's an e to the x in both terms. You can factor that out. So there's sort of an easier way to write this answer in terms of algebraic simplification, right? But they're both answers. This is okay. This is okay. You've completed the product rule as soon as the differentiation is over. Okay, let's do a couple of more. I'm going to talk fast. You can pause these things. Always go at your own pace. Jot down some questions, maybe for me in my Zoom office hours. But to keep the videos short and easier to focus on, I'm not going to. I'm actually doing a bad habit right now. I'm wasting time. I should just keep moving. Okay, so here I've got a function f of z. You can see that it's a product of these things, and I want to compute its derivative. We could expand f of z out if you want first, so we could multiply this thing out, but we're not going to be able to avoid the product rule because we're going to get things like e to the z times z, e to the z times e to the z. So we might as well just use the product rule in this form. All right, so once again, let's write it out. The input variable this time is called z. So the product rule goes take the first factor, undifferentiated, multiply it by the derivative of the second factor. And then reverse the process. Differentiate, pardon me, the first factor. Leave the second factor undifferentiated. So there I'm just focusing on the product rule pattern. Now I'll focus on what the derivatives of the individual components are. So 1 minus e to the z, nothing going on with it, but it's got to come along for the ride. And then the derivative of z plus e to the z using the sum rule, well, it's the derivative of z, that's 1, plus the derivative of e to the z, that's e to the z. Likewise, the sum rule here, the derivative of 1 is 0. Subtract the derivative of e to the z. This term is undifferentiated. That's my answer. It's my answer, not simplified. I'm not going to simplify this thing completely here, I think, in the name of moving on and doing more examples, but let me just rewrite this as 1 minus e to the z times 1 plus e to the z, and then 0 minus something. It's just the negative of that thing times z plus e to the z. And I don't see any common factors in that thing. We could expand it out, but I'm gonna leave it here for this purpose of that example. So 2 illustrations of the product rule. Cool. All right, I'm not going to derive it. But similarly, the quotient rule, the rule for differentiating a fraction, you have 2 differentiable functions, F and G are both differentiable, and I want to differentiate a fraction, F over G. So F is the numerator, G is the denominator. Okay, the quotient rule says that F over G is differentiable as long as G isn't 0 at X. The formula works like this. It's a little bit more complicated. In the Leibniz notation especially, it looks very complicated. I think I like these primes. So notice that it's sort of like the product rule, in that in this numerator, we're differentiating one of the functions and not the other, both possible ways. But unlike the product rule, we have to be careful about the order, because these things aren't added together, they're subtracted, right? So subtraction is sensitive to the order in which you write these things. So I'm just writing it exactly like your book does. The author writes the denominator times the derivative of the numerator minus the other way around. So that's how I've written it as well. So that's the quotient rule. You'll get used to this pattern. When you're first using it, you'll have to, of course, refer to this over and over and over again. But after several applications of it, maybe 10, 12, I don't know, it depends on you, you'll get this pattern down. Let's try it. Let's try it. Let's see if I can leave, well, at least my prime version in view as we start to make this computation. Quotient rule computations take a lot of room. Give yourself a lot of room on the paper. So I want to take the derivative of x squared minus 2 over 2x plus 1. It's perfect for the quotient rule because the numerator and denominator of those are differentiable, and I know how to differentiate them. Okay, so how does the quotient rule work? Well, you square the denominator, 2x plus 1 squared, and you put it downstairs, and then you write that denominator down on the far left. So that's your G undifferentiated. Yeah, so that's this part of the formula. G squared G, and then I multiply that by the derivative of F. So x squared minus 2 prime. Okay, and then subtract the numerator times the derivative of the denominator. So there's the quotient rule pattern. G F prime minus F G prime over G squared, where F and G are the numerator and denominator respectively. And now, just like with the product rule, now we focus on the derivatives. Okay, 2x plus 1 is nothing happening to it. X squared minus 2's derivative is 2x. Be careful with signs here. You're subtracting things with more than one term. You got to get the signs right, but I'm going to write this as minus the quantity x squared minus 2. The derivative of 2x plus 1 is 2. I'm going to divide all of that by 2x plus 1 squared. All right, and for purposes of differentiation, we're done. But maybe you want to simplify that thing just a little bit. Let's do it. Just quickly, if we multiply out the numerator, what would we get? Well, we could factor out a 2, I think, to make this more efficient. But let me just do it. So if I multiply out the numerator, 2x plus 1 times 2x is 4x squared plus 2x. And then I'm going to be subtracting 2x squared, right? Watch this minus sign. Adding 4. So you got to make sure to get the signs right. You can organize this algebra in different ways. It's okay. And now just combining some like terms, I see that, well, 4x squared minus 2x squared simplifies to 2x squared. I've got a 2x, a minus 4. And then other than factoring out a 2 out of that numerator, I don't really see any way to simplify that further. So we'll be content with that. Last example, trying to circle back through some old ideas here. You're going to need to practice these product and quotient rules on the activity and the homework to get confident at them. But let's see what this example is all about. So it's asking us to, let me scroll down a little bit, find the equation of a tangent line to the function f of x equals 2x times e to the x at x equals 0. And then subsequent question, does f have any horizontal tangent lines and where? Okay, so what's the review concept I'm talking about here in this example? Equation of a tangent line. Equation of a tangent line means that we got to have the slope, right? Slope is the derivative. So we're going to want to calculate the derivative of that function at x equals 0. And then the second question it's asking, does this thing have any horizontal tangent lines? That's best answered with a graph. Yeah, so I've got a graph. You already saw it. Let me scroll up a little bit here. You're looking at a graph of 2x times e to the x in this picture. If I hide the question up there a little bit, you can see the graph a little better. And yeah, I can see that there's a horizontal tangent line. There's a horizontal tangent line on that graph. It looks like at a point that's about right there. If you can see the scale in the graph, you even have a guess for what that x value is, but the calculus can tell us that. All right, so let's do this first part first. Let's find the derivative so that we can get our slope, and we're going to get this tangent line at x equals 0. You need to see the formula of the function again. So I'm looking right here when I'm going to differentiate this thing. And what do we got? We're going to use the product rule. Well, we're going to use the constant multiple rule too. This function has a 2 in front of it. So I'm going to put that 2 all the way out front, and now use the product rule pattern. The product rule pattern is you take the first function times the derivative of the second, and then you add to it the derivative of the first function times the second undifferentiated. Yeah? So if we put that information in, that's 2, doing the derivatives, I mean, that's x times e to the x. Derivative of x is 1. So we get that. We get 2 times the quantity, x times e to the x plus e to the x. Yeah? And we want the tangent line at x equals 0. So we want to compute f prime of 0. So when you plug in 0 in there, you get 2 times the quantity, well, 0 times e to the x, or e to the 0 is 0, plus e to the 0, which is 1, right? E to the 0 is 1. Any exponential function has y-intercept 0, 1. So our slope is 2 times 1, or 2. All right? So that's going to be our slope. That's our tangent slope. What about our point? You can see it on the graph, but the point is the point 0, f of 0. So that's 0, if you plug in 0 to f of x, you also got 0. I know you can't see, well, you can't see the f of x formula. It's right over here. So plugging in 0 in that thing is going to give 0 because of this factor. It's 2 times 0 times 1. So our point is just the origin. So we want a line through the origin. Oops. We want a line through the origin. So the y-coordinate is 0 and the slope is 2. So I'm writing y minus the y-coordinate that I know is 2 times x minus the x-coordinate that I know. And if you simplify that, that's the line y equals 2x. Okay, we could switch over to a Desmos window and graph that line y equals 2x on the same screen, and we will see that it looks tangent. I'm just going to write it in the picture right there. But I encourage you to look at these things with all of this technology. It'll reinforce these ideas. So there's our first part. So sorry, I'm kind of all over the place in this example, but find the equation of the tangent line at x equals 0. You can just write the answer here in a different color. We derived all the details down below. That tangent line has the formula y equals 2x. Does the f have any horizontal tangent lines? Yes, from the graph. Where? Well, we got to know where the tangent slopes are 0. So we're going to translate that question, where does f have horizontal tangent lines, into the question, where is the derivative of 0? Where is the derivative equal to 0? Sorry, horizontal tangent lines is the same as, that's all I mean by that, f prime of x equaling 0, right? We have an expression for f prime of x. It was 2 times e to the x plus e to the x. So we need to know, how can 2 times x e to the x plus e to the x equal 0? All right, well, you can divide both sides of that equation by 2 and factor out an e to the x. So it's equivalent to the equation e to the x times x plus 1 is 0, right? E to the x is never 0 for any value of x. So this is 0 only when x plus 1 is, right? And x plus 1 is 0. I'm going to go over here so I don't go on to the next page. Only when x is minus 1. So our function has exactly one horizontal tangent line, and it's when x is equal to minus 1. And if we return back to the picture, we can see that. I kind of made this picture a little messy. I'm going to get rid of some of my mess here. But yeah, I can look at this graph, and it seems to me that there is precisely one horizontal tangent line. And that horizontal tangent line happens when x is equal to -1. We just computed it. Okay, thanks for listening.